This is Rahul from group number 7, that is from room number 203 to 209. And the topic of our group is reciprocating pumps. And my roll number is 2K20 ME204. So now let us start off the topic. So first let us give a little introduction of what is a reciprocating pump. So a reciprocating pump is basically a machine that moves a fluid by means of the reciprocating action of a piston or a plunger inside a cylinder. Reciprocating pumps are positive displacement pumps. To better understand this, let us use a video. So these are basically the components inside a reciprocating pump. First is, as you all know, a piston, then a cylinder. The piston is connected to the crankshaft through a connecting rod, and the crankshaft is connected to a motor. So the first thing that basically happens in it is that the motor rotates the crankshaft, and the rotary motion is converted into reciprocating motion by the crankshaft. The reciprocating motion is then transferred to the piston through the connecting rod, which we will understand by the animation. See, as you can see that the crankshaft is going reciprocating motion and the piston goes in the reciprocating manner. First it goes left and then it goes right. These are the two valves that are connected at the extreme left position of the cylinder. These are non-return valves. The bottom one is the suction valve and the upper one is the delivery valve. So basically, when the piston moves to the rightmost position from left to right, okay, so what happens is that a low pressure is generated in the region. As you can see above the suction valve, there is low pressure created. So from this sump, the water is pumped into the cylinder. After that, the cylinder goes to the piston goes to the extreme right position, from which you can see that all the water from the sump has been taken into the cylinder. After this point, the suction valve closes and the delivery valve that is closed opens. Okay, so here you can see that the suction valve is closed and the delivery valve opens. So here the compression of the water takes place, and after that the water is then discharged through the delivery valve into the tank. The idea that is given is the reciprocating pump is basically of two types. First is single acting reciprocating pump, and the second one is a double acting reciprocating pump. The example that I have shown you right here is a single acting reciprocating pump. In single acting reciprocating pump, there is actually a time discharge. As you can see here, the suction valve opens, then the delivery valve opens. So the supply of fluid is not actually constant. We do provide some mechanism so that it can be constant, but it's not 100% constant at the same time. Now I will be talking about the second type of reciprocating pump, that is the double acting reciprocating pump. So the double acting reciprocating pump has the same mechanism as that of a single acting reciprocating pump. Only the difference being that in its extreme right position, two more valves are being opened. In the double acting reciprocating pump, the cylinder is divided into two chambers. Okay, and now in the first motion, in the animation you can see in the first one, that is when the piston moves from left to right, the suction valve opens in the first chamber, and through the sump the water is being pumped into the cylinder. After that, it goes into compression and the discharge valve opens and the suction valve of the first chamber closes. Now simultaneously, as you can see in the second chamber, the suction valve opens. Okay, because due to the pressure, there is a low pressure that is being generated at the extreme right position, that is here. Okay, so now the delivery valve of the first chamber is opened and the suction valve of the second chamber is being opened at the same time. After this, as you can see, the discharge valve closes of the first chamber and the discharge valve of the second chamber opens, and the suction valve of the first chamber opens once again. So it is a simultaneous process in which, suppose when the piston is moving from left to right position, okay, at that point of time, in the first chamber the inlet valve is opened and discharge valve is closed, as in a single acting reciprocating pump. But when the piston moves from right to left once again, a low pressure is being generated at the right extreme right position, and there is also an inlet valve there which is opened. So due to the low pressure being generated there, the water from the sump comes in through the second chamber inside the cylinder. After that, it goes into the extreme left position. Okay, at the extreme left position, once again all the suction is being done at the second chamber, and the compression takes place and discharge of the second chamber opens. So the water through the discharge valve goes into the tank once again. So this is a double acting reciprocating pump. Now let us come to the PPT once again. Here I am basically showing the working I have already explained with the help of the video. Now what I am basically showing you here is the graph. That is the graph which shows the discharge versus crank angle for a single acting reciprocating pump. Now for a single acting reciprocating pump, in the first stroke, that is when the piston moves from left to right, the crank moves from 0 to 180 degree. At that moment no discharge is taking place. So for that period of time the discharge value is 0. So there is nothing in the graph. After that, when the piston moves from right to left, the crank moves from 180 to 360 degree. So at that point the discharge is taking place because the discharge valve is open at that time. And at the midpoint of the cylinder, the discharge is at maximum point. Is maximum. So for that, the discharge at 270 degree is maximum, as you can see from the graph. So we get a parabolic shape from 180 degree to 360 degree. Now here what I've basically shown you is the discharge versus crank angle for a double acting reciprocating pump. So for a double acting reciprocating pump, while in the first chamber, that is when the crank is from 0 to 180 degree, the piston moves from left to right. In the first chamber, suction is taking place. So even so, if the suction is taking place and at the first chamber and no discharge taking place there, but in the second chamber, as I've shown you in the video, the discharge valve is open at that moment or point of time. So because the discharge valve is open, discharge is taking place, so discharge value is given. And at the midpoint, once again the discharge is maximum. After the crank moves once again from 180 to 360 degree, the value of discharge at 270 degree is once again maximum because the discharge valve is opened at point 1, so discharge is also taking place at that point. Now here is the classification. So first type of classification of reciprocating pump is basically on what type of what is driving the pump. First is direct and second is indirect acting pump. So some pumps are driven directly by a prime mover such as steam engine, which itself has a reciprocating motion. In such a case, the piston rod of the steam engine is directly connected to the plunger. Such pump systems are called as steam driven reciprocating pump. As you can see from the diagram, this is a steam driven reciprocating pump. Now sometimes often happens that we don't have a direct supply. So what we have basically got is an electric motor or an IC engine which gives us the power. So that type of reciprocating pumps are known as power driven reciprocating pumps. Now the second type of classification is based on the number of cylinders, the number which are basically single cylinder, double cylinder and multi-cylinder pump. So in a single cylinder pump there will be only one cylinder. One cylinder pumps are called simple pumps. In a double cylinder there will be two pumps. Okay, as you can basically learn from the term itself, that is double cylinder. Okay, the suction power of two cylinders will be connected to a common suction pipe, and the outlets of the two cylinder will be connected to a common delivery pipe. This type of pipe is known as two-throw pump. Now multi-cylinder pump are the pumps in which we have multiple cylinders. Okay, in this type of pumping arrangement is basically employed to get more steady flow in the delivery pipe. It is the most complex but also the one that gives us the most the steady supply of the water into the tank. Now third type of classification is basically vertical or horizontal. This classification basically depends upon the mounting of the pump. The reciprocating pump can be mounted either vertically or horizontally depending on the space and other operational features. The third type of classification is low pressure or high pressure reciprocating pumps. Now reciprocating pumps are employed for low discharge under high pressures, the pressure ranging up to as much as 150 atm. Hence the terms low and high are relative terms. Generally, pressures up to 50 atm are treated as low pressure reciprocating pump, and pressures higher than that are treated as high pressure reciprocating pumps. Now, this is basically common mistake that most of people make is the difference between a piston and a plunger. So now, in connection to a reciprocating pump, the term piston plunger I use interchangeably. Then their function is mostly the same, but they do have a difference between them. So for a plunger is a smooth cylindrical rod attached to a slider or rod mechanism. A stationary steel is used around the plunger and the plunger moves through the stationary seal ring. While a piston consists of a cylindrical disc provided with the seal at the outer diameter, the piston is attached to a smooth rod called piston rod that imparts reciprocating motion at the liquid end of the piston. The seal in the piston top moves the piston. For the plunger, because of this construction, plungers are single acting. For a double acting mechanism with plungers, 2 cylinders are required, and plungers are only used for high discharges, which are usually greater than 50 atm. Piston can be used for low pressure also, that is about less than 50 atm and relatively high flows. The further pistons are used in both single acting and double acting pumps. That will be all from my side. Thank you.
We will be talking about here. So let L be the length of the stroke, A be the cross section of area of cylinder, and N be the speed of the crank. Speed of crank in RPM. So firstly coming single acting pump. Consider a single acting pump in one stroke. Single acting. So in one stroke, the volume displaced is equals to A into L, which is area into length of the stroke. So therefore discharge of the pump equals to Q is equals to A into L A into N upon 60. Now coming to double acting pump. In double acting pump, both sides of the pistons will be displacing the liquid. In one evolution of the crank, volume of liquid displaced is equal to A into L, which is the left side of the piston, plus A minus AP into L, where A minus AP is the area of piston from the right side minus the area of where AP is the area of piston rod attached to one end of the piston to connect it to the crankshaft. The pumps makes n revolutions per minute, and hence discharge of the pump is equals to Q, which is equals to 2 into A minus P into L into N upon 60. So if the area of the piston AP is very small in comparison to the area of cylinder A, then equation 6.2 can be approximated as Q is equals to 2 into A into L into N upon 60, which is nothing than 2 times the discharge of single acting. Now coming to volumetric efficiency. So as above discussed, equation 6.1 are the theoretical discharge of an ideal single acting and double acting pump recipe. The actual discharge of a pump may be less than the value given by the equation. This may happen for the following reasons. Firstly, to be major cause of slippage of fluid back past the pump valves because they can be closed or sealed. This will vary between 1.1 to 5% based upon the pump speed and valve design. Now, the volumetric efficiency of the pump in this percentage is defined as eta V is equals to actual discharge upon theoretical discharge into 100 upon which is equals to QA upon Q actual discharge upon theoretical discharge into 100. Now coming to second, coefficient of discharge. The ratio of actual discharge to the actual discharge to the theoretical discharge is known as the coefficient of discharge, CD, and thus CD is equals to actual discharge upon theoretical discharge. Now coming to velocities and discharges. The displacement of piston from end of the stroke, which is equals to x, is equals to r minus r cos q, which is equals to r minus r cos omega t, which is we have calculated through the crankshaft angle and the displacement of the piston, which has caused the displacement of piston. So the velocity of piston becomes v equals to dx upon dt, which is omega r sin omega t equals to omega r sin q. If A is the area of the piston and A1 is the area of pipe, suction or delivery, velocity of water at any state V1 is equals to A1 upon A1 omega r sin omega t, which is thus equals to A upon A1 omega r sin t. So the maximum velocity in the pipe, by differentiating more further, we have calculated, which is equals to V1 max because A upon A1 omega R. So mean velocity in single acting pump is calculated by this formula we have shown here, which gives us the result V1 max upon pi, and thus average time velocity in the pipe V1, which is in the pipe which is V1, is equals to A upon A1 omega R by pi. Also from the above equation, the ratio of maximum discharge Q max to mean discharge Q, the delivery pipe, is equals to Q upon Q max, which is equals to V1 upon V1 max, which is thus equals to 1 upon pi. We have also calculated the acceleration of piston. So acceleration is other than dV by dt. By calculating dV by dt, we will get the acceleration of the piston, which is equals to omega square r cos omega r cos theta. Theta is the angle of crankshaft. Acceleration of liquid in the pipe suction area and this is equals to A1, which is equals to A upon A1 omega r cos theta. Now coming for speed for double acting pump. So for double acting pump, the mean velocity of the flow in one complete revolution of crank is given by V1 is equals to V1 max by 2 pi integration pi to 0 sin theta. Thus integrating sin theta, we get minus cos theta pi by theta into 2V1 max by 2 pi, which is equals to 2V1 max by pi. So the ratio of V1 by V1 max equals to 2 by pi. Now coming to variation of discharge in multi-throw pumps. By careful tracking of discharge in various cylinders at different crank angles, the flow variation in multiplex pumps can be worked out. Different figure shows the variation of single, double, three throw pumps. Extend the variations of discharge as ratios of the average discharge. The theoretical flow variation is various commonly used in multiplex pumps are represented. Here the table shows different values of the discharges in different types of pumps, reciprocating pumps. This table clearly shows the advantage of multiplex pumps in obtaining uniform flow in the delivery track. Analysis of the flow variation in double-acting multiplex pump indicate that accepting the analysis of the flow variation in double-acting multiplex pumps indicate that accepting the simplex pump. So that's all for my side.
Hello, my name is Puneet, roll number 2K20ME20, and today the topic which I am going to explain is acceleration head. So first I will tell you about what is acceleration head. Acceleration head is the energy required to change the velocity of the liquid in the system from an at rest or zero condition to some non-zero value. Now I will tell you about the principle of acceleration head. When crank will start to rotate, piston will be started to reciprocate in the forward and backward direction within the cylinder at the two extreme position, inner dead center and outer dead center. The velocity of piston will be zero and velocity will be maximum at the middle of stroke, which is known as center of cylinder. We can say that at the start of stroke, suction or delivery velocity or piston will be zero and it will be increasing and will be maximum at the middle of stroke, and again it will be decreasing, and finally velocity of piston will become zero at the end of the stroke. Therefore, at the start of suction, stroke or delivery stroke, piston will have acceleration and this acceleration will be decreasing and will be zero at the middle of stroke. Further retardation will be started and retardation will be maximum at the end of the stroke. In simple, piston will be having acceleration at start and then stroke, and piston will be having retardation at the end of the stroke. As water in the cylinder will be in contact with the piston, and therefore velocity and acceleration of water in suction and delivery pipe will be dependent over the velocity and acceleration of the piston. Therefore, water flowing through suction and delivery pipe will also have acceleration at the start of each stroke and will have retardation at the end of. Hence, velocity of liquid water in suction and delivery pipe will not be uniform. Therefore, acceleration head and retardation head will be acting on water flowing through the suction or delivery pipe. Pressure inside the cylinder will be changing due to this acceleration head or retardation.
And if length of connecting rod is much larger than the radius of crank, or we can also say that if ratio of length of connecting rod to crank radius is very large, then motion of piston inside the cylinder could be considered as simple harmonic. And now I will tell you about the derivation. So let's of crank, and now as we can see, the acceleration of fluid in the pipe requires a force F, which is given by rho area of cylinder 1 into length of cylinder 1, into area of cylinder upon area of cylinder 1 omega square r cos theta, and the pressure head caused by this force is acceleration head equals to force upon rho into gravity into area of cylinder 1 equals to length of cylinder 1 upon gravity into area of cylinder 1 upon area of cylinder upon area of cylinder 1 omega square r cos. And now I will tell you acceleration head for suction pipe. Acceleration for head for suction pipe is equals to Ls upon G A upon As omega square r cos theta, in which Ls is length of suction pipe, G is gravity, A is area of cylinder, As is area of suction pipe, and omega is angular speed of crank in radian or second. So the maximum acceleration head for suction pipe is at the commencement of the stroke, which is at theta is equals to 0, and is given by Ls upon G A upon As omega square r. And at the end of suction stroke, when theta is equals to 180 degree, at the end of suction stroke when theta is equals to 180 degree, acceleration head for suction pipe is minimum, and which is minus Ls upon G A upon As omega square r. Also, at the middle of suction stroke when theta is equals to 90, acceleration head for suction pipe is equals to 0. And for delivery pipe, acceleration head for delivery pipe is equals to LD upon G A upon AD omega square r cos theta, in which LD is length of delivery pipe upon gravity into area of cylinder upon area of delivery pipe. At maximum acceleration head for delivery pipe is at the commencement of the stroke, which is at theta is equals to 0, and is given by LD upon G A upon AD omega square r. At the end of delivery stroke when theta is equals to 180 degree, acceleration head for delivery pipe is minimum, and is LD upon G A upon AD omega square r. And also at the middle of delivery stroke when theta is equals to 90 degree, acceleration head of delivery pipe is equals to 0. And now correction for non-simple harmonic motion. The flow of liquid in suction and delivery pipes causes a friction loss, and the pump has to provide power to overcome this loss. The friction loss HF is calculated by using Darcy-Weisbach equation in the same form as is used in steady flow in the pipes. Thus, HF is equals to FLV square upon 2GD, where F is Darcy-Weisbach friction factor, V is average velocity in the pipe, and D is diameter of the pipe. In the present case, time average velocity in the pipe given is used, and friction factor as given typically in Moody's diagram is used. And now correction for non-simple harmonic motion for suction pipe. Where frictional head loss HFS is equals to FLS upon 2G ds A upon AS omega r sin theta का whole square. Since HF is function of 2 sin 2 theta, the frictional head loss varies parabolically with theta. This gives the average value of head loss in friction as 2 by 3 times. This gives average value of head loss in friction as 2/3 times the maximum value of frictional loss of head. Maximum head loss due to friction in such pipe occurs at theta is equals to 90 degree, and its value is given by FLS upon 2G ds A upon AS r omega का whole square. Thus the average frictional head loss in suction pipe is given by 2 by 3 HFS is equals to 1 by 3 FLS upon G ds A upon AS omega r whole square. Now the combined effect of static acceleration and friction heads. In a simple reciprocating pump, the pump has to produce enough head to overcome static head, friction head, and acceleration head at both suction and delivery pipes. Considering the suction pipe first, the total head loss in suction pipe measured as absolute pressure head is The total head in suction pipe is measured as absolute pressure head. Is HTS is equals to H atmospheric pressure. Now combined effect of static acceleration and friction heads. In a simple reciprocating pump, the pump has to produce enough head to overcome static head, friction head and acceleration head at both suction and delivery pipes. Considering the suction pipe first, the total head in suction pipe measured as absolute pressure head is HTS is equals to HAMT minus HS plus HAS plus HFS, where HAMT is atmospheric pressure, HS is equals to static suction head, HAS is equals to acceleration head in suction pipe, HFS is equals to average friction head in suction pipe. Similarly, in delivery pipe, the total head in delivery pipe measured as absolute pressure head is HTD is equals to HAMT plus HD plus HAD plus HFD, where HAMT is atmospheric pressure, HD is equals to static delivery head, HAD is equals to acceleration head and delivery pipe, and HFD is equals to average frictional head and delivery pipe. It is to be noted that while the static heads HS and HD remains constant for particular installation of the pump, the other two terms, namely the acceleration head and friction head, are functions of the time. Theta, which is theta is equals to omega into time and vary from instant to instant. The salient features of the total suction and total delivery pressure heads at three values of theta are summarized in table.
Hello everyone, this side Rahul Kumar Srivastav, having roll number 2K20 ME205, is here to discuss about the indicator diagrams. So basically an indicator diagram of a reciprocating pump is a plot showing the variations of pressure in the cylinder, the displacement of the piston, and at various stages of the piston strokes. The area of the indicator diagram represents the work done by the pump per unit weight of the liquid in one complete revolution of the crank. Figure 1 shows a theoretical indicator diagram of an ideal reciprocating pump, a pump with no acceleration head and of no frictional losses. The ordinate represents the pressure heads on the plunger and the abscissa, the displacement of a plunger of a unit length. The horizontal line, that is 0 0, as it is shown here, 0 0 datum line at the bottom of the figure represents the absolute zero pressure head, which is taken as the datum for pressure heads. Line AB represents the atmospheric pressure. HATM link JK, that is represents the suction stroke. Point J representing theta equals to 0, and at point K, which is representing theta equals to 180 of the suction stroke. The suction head developed at the cylinder inlet is HS at location J, and it remains constant all along the stroke till the end point K. Now the point I marks the beginning of the delivery stroke with Q is equals to 0 as shown over here, and at that point the pressure head in the cylinder is HD and the head developed remains constant till the end of the delivery stroke at M, at which theta is equals to 180 degree. The pressure head HD, which is above the atmospheric pressure and is marked accordingly in the figure. The stroke length, which is equal to the length of the plunger, is taken as of unit dimension. Area JKBA, that is JKBA, is equals to HS, which is equal to the work done per unit weight of the fluid in a suction stroke. Similarly, area ABL, that is the ABL and M, is equals to HD, which represents the work done per unit weight of fluid in delivery stroke. Hence, total work done per unit weight of fluid is equals to area of JKBA plus area ABLM, that is equals to HS plus HD. If the area of the cylinder is A and the stroke length is L, then the weight of the liquid pumped in one revolution of crank, that is YAL. Work done per revolution of crank YAL HS plus HD. Now the theoretical work done per second is equals to PT, which is equals to YALN divided by 60 multiplied by HS plus HD. Now let's start the indicator diagram with having having acceleration effect but no friction effects. So let's consider a single acting simplex pump with acceleration effect but without friction. First stroke, it is suction stroke. Equation gives the acceleration in the suction pipe at any instant acceleration head for suction pipe at HAS, which is equals to LS divided by G multiplied by A divided by AS multiplied by omega square r cos theta. The maximum acceleration head for suction pipe is at theta is equals to 0, that is at the beginning of the stroke, and is given by HAS, and that is LS by G multiplied by A divided by AS omega square r. Also at the middle of the stroke when theta goes to 90, and which is and at theta goes to 90 HS goes to 0, the acceleration head is added to the suction head HAS, and at the beginning of the stroke, and at the 180 degree theta HAS, which is minimum. So being deceleration effect is deducted from the suction head HS, the resulting variation of the net suction pressure head inclusive of the acceleration head is shown by the line PQ in figure 2. The line PQ is shown over here. So the suction stroke that includes the acceleration effect is APQB. It is A, P, Q and B. Note that the triangular portions JPP1, that is JPP1 and P1KQ are identical and hence are of equal area. Hence area APQB, which is equals to area AJKB, is equals to HS multiplied by 1, which is come out to be HS. In the second stroke, that is the delivery stroke, the column or the water in the delivery pipe will be accelerated at the beginning and the first half of the delivery stroke. It will be deaccelerated at the second half of the stroke until the end of the stroke. The acceleration head for the delivery pipe is given by the equation HAD, which is equals to LD divided by G multiplied by A divided by AD is omega square r cos theta. Now, HAD is maximum at the beginning of the delivery stroke, that is theta is equals to 0, and the maximum value is given by the equation HAD LD by G multiplied by A divided by AD multiplied by omega square r. Also at the middle of the stroke when theta is equals to 90 and HAD is equals to 0, and this is indicated by the point as shown over here. The rectified indicator diagram of the delivery stroke accounting for acceleration effect is the area ABRS. Hence area ABRS and area ABLM indicates that the acceleration does not change the total work done in the delivery stroke, but only alters the distribution of the pressure head at various displacements of the delivery stroke. Further, the area PQBLRSA in the last figure, that is this, single stroke reciprocating pump without friction. Now indicator diagram having both acceleration and friction effects. So coming to first stroke, that is the suction stroke. When the friction effects in the suction pipe along with the acceleration effects are considered, the additional head losses due to the frictional effect has to be superimposed on the indicator diagram of figure 2. The frictional head losses in the suction pipe is given by the equation HFS FLV square multiplied by divided by 2GD is equals to FLV square divided by 2GD multiplied by A divided by AS omega r square sin theta. Now the average frictional head losses in the suction pipe is given by the equation, that is the average HFS was to 2 by 3, which is of 2 by 3 of HFSM. Now at the beginning of the suction stroke, that is theta goes to 0, and at the end of the suction stroke, that is theta goes to 180, the frictional losses, that is HFS, is 0. The maximum ordinate is HFSM, which is occurs at the mid suction stroke, that is at the point E of the figure 3 as shown over here. The corresponding to theta is equals to 90 degree. Thus at the beginning of the suction stroke, the total suction head is HS plus HS, and at the end of the suction stroke, it is HS minus HS. Now the delivery stroke, the head loss due to the friction in the delivery pipe is given by the equation HFD, which is equal to FLV square divided by 2GD, which is equal to FL2GD A divided by AD omega r square sin theta. Since HFD is a function of sin square theta, the frictional head losses in the delivery stroke varies parabolically with theta. Further, the average value is 2/3 times the maximum value, and the average frictional head losses in the delivery pipe is given by the equation 6.22, as it is discussed as average, HFD is equals to 2 by third of HFDM. The indicator diagram for the delivery stroke will have the extra head HFD, which is added to the indicator diagram of figure 6.5. This figure 6.5. The resulting indicator diagram of the delivery pipe is shown in figure 6.6. The parabola RFS reflects the rotational effects. The maximum of this parabola occurs at point F corresponding to Q equals to 90 of the delivery stroke. Now the theoretical work done per second. The total work done per unit weight of the liquid pumped in one complete revolution of the crankshaft is the sum of the areas of the indicator diagram of suction and delivery stroke, and is given by the areas represented by APEQ PRFS of figure 6.6. This is equal to HS plus 2/3 of HFSM plus HD plus HFS DM. Now, if n represent the speed of the pump in revolutions per minute, then Pt is equals to YALN divided by 60 multiplied by HS plus 2 by third of HFSM plus HD plus HFSDM.
Hi everyone, my name is Ram and I am going to present on characteristics of reciprocating pump. General characteristics. They are efficiency. There are two types of efficiency, volumetric efficiency and mechanical efficiency. The volumetric efficiency is essential due to slippage at valves and seals. Mechanical efficiency arises due to friction at bearing and at speed reducing devices. Thus, efficiency of a reciprocating pump is normally very high, being of order of 85 to 90% in a well-maintained pump. Second, pressure. Capacity to produce high pressure is a special feature of reciprocating pump. Pump with pressure up to 70 bar are routinely used. Special pump can have pressure at as high as 400 bar. Third, priming. The reciprocating pump is self-priming. However, where possible to reduce wear or the risk of seizure, it should be flooded with liquid before starting. Now, fourth, pressure pulsation. Pressure pulsation is inherent in the reciprocating mechanism. Flow variation is an indication of scope of pressure fluctuation. Pressure fluctuations are a product of acceleration created by the pump. A pulsating pump flow may require special design consideration in the piping system to avoid vibration of piping and consequent failure of system component by fatigue. Fifth, power. The power rating of reciprocating pump vary depending upon the application. It varies from as low as 0.25 kW to high value of order of 2500 kW. Sixth, capacity. A reciprocating pump produces constant flow of for a given speed, irrespective of the viscosity of fluid and downstream pressure condition. This fact makes it an excellent choice of metering and dosing purpose. The discharge capacity has a wide range, anywhere from a few liters per hour used in metering pump to order of 0.5 meter cube per second in mass conveyance pump. Speed. Reciprocating pump are essentially slow speed pump. Usual speed cover a range from about 100 rpm up to 700 rpm. Reducing gear are invariably used when the prime mover is an electric motor or an IC engine. Now coming to the application. Industrial use. General reciprocating pump can handle a full range of liquid from low viscosity chemical to high viscosity material like heavy oils, from clean water to high particle content slurries including concrete. In the view of the wide operating range, reciprocating pumps are often offered choice for difficult applications, especially when the discharge are low and pressure are high. Oil and gas. Second, food and food processing. Third, mining. Fourth, water treatment plant. Now coming to the operational characteristics. The operational characteristics of reciprocating pump are considered in four groupings as indicating below. First, variation of discharge and power with speed. The capacity Q, flow rate of reciprocating pump varies linearly with speed. Here the two lines one for zero slip and another for positive slip, which is usually less than about 3%, are shown in the figure. Second, variation of flow rate with pressure head. Here the graph shows that the flow rate is constant at all values of head. This consistency of flow rate regardless of head is a typical characteristic of a reciprocating pump. The flow rate of a reciprocating pump can be varied only by changing the speed of or displacement. A pressure relief valve determines the maximum pressure head that can be attained in a pump setting. Third, variation of efficiency with head. Figure C shows systematically the variation of efficiency of a reciprocating pump with head. It is seen that the efficiency is constant over a wide range of head. The corresponding variation of efficiency of centrifugal pump with head is shown as a dotted line. Fourth, the effect of viscosity. In the figure A, showed the variation of efficiency of a reciprocating pump with viscosity of the fluid. If some pump in a particular range, the efficiency may in fact improve with increase in the viscosity due to reduction of leakage, but in centrifugal pump show decrease in the efficiency with increase in the viscosity of the liquid. Figure B represents a plot of head against flow rate at constant speed over a wide range of viscosity. As indicated in the figure, the reciprocating pump exhibits constant flow rate over a broad range of pressure head. There is a very little effect of viscosity on the flow rate. These characteristics make reciprocating pump a better choice when high viscosity liquid are to be pumped. Now coming to the cavitation. Since we are concerned with liquid as a pumping medium, the fluid should be in the liquid phase throughout the pumping system. At any point in the suction line, the pressure should be high enough so that the vapor bubbles do not form in the pipeline. If at any point the pressure falls to a neighborhood of vapor pressure of liquid, the dissolved gases would first separate from the liquid. This process is called separation. The separated gas may form pockets that would lead to the flow discontinuous, leading to loss of efficiency. If the pressure at any point in the pipeline falls to the level of vapor pressure of the liquid material, it will release bubbles and transport it to higher pressure region. In the region of higher pressure, these vapor bubbles may collapse, leading to cavitation phenomena and cavitation damage. When the cavitation occurs, the performance of the pump is severely degraded. The volume rate of flow drops, pump becomes noisy, erosion or plunger, packing area and non-return valves take place. Now coming to NPSH, net positive suction pressure required. The pump manufacturer through tests in the laboratories determine the suction pressure required to avoid cavitation for each pump design. The result is indicated as NPSHR, net positive suction pressure required, for the pump at designated operating pressure head and a discharge. NPSHR for a reciprocating pump is defined in a slightly different way than that for a centrifugal pump. For reciprocating pump, it is defined as the head in absolute unit, measured above the prevailing vapor pressure head, required by the pump to obtain satisfactory volumetric efficiency, usually no more than 3% reduction of capacity, and prevent excessive cavitation. While NPSHR is a characteristic of the pump, NPSHA is dependent on the pump setting and pump operating characteristics. It is the head in absolute unit, measured above the prevailing vapor pressure head, availing to the pump at the pump inlet. With the usual notation, it could be shown at given below equation. Now pump installation. The installation of pump should be such that to achieve the NPSHR of the pump with margin M, the net positive head available at the site is NPSHA. The difference between NPSHA and NPSHR is the margin M. The usual practice is reciprocating pump is to provide a margin M as a percentage of NPSHR or 1.5 to 3.5 mm, depending upon the type of liquid, type of pump, and recommendation of the manufacturer. The objective of the pump setting is to have maximum NPSHA at a given location. The following are the possibilities to maximize NPSHA in the setting of reciprocating pump. Reduce the suction lift HS. Second, reduce friction loss. Toward this, reduce suction pipeline or maximize the suction pipe diameter or minimize the number of bands, tees and wheels in the suction pipe. Third, increase absolute pressure if possible. Fourth, use multiple pumps. Fifth, use air vessels and such other pulsation reducing device in the suction pipe. Thank you.
Air vessels, what are air vessels and where they are located, about the use and basics on their equations used for air vessels. So first of all, we will discuss about what's the flow dampening, because that's why the air vessels are used. So for a flow acting for flow from a single acting reciprocating pump is highly fluctuating, and the delivery pipe carries the flow only one half of the cycle. In the remaining part of the cycle, which is during the suction stroke, the delivery pipe does not carry any flow at all. This results in a highly variable discharges rate in the pipe, and the high variation of the flow in each cycle of the crank leads to not only undesirable flow of characteristics but also uneconomical pipe design at the pipe, which have to be designed to carry the maximum flow safety. An economical alternative for the flow damping is to use special devices called generic name flow dampers. These devices are used as an attachment to all the type of reciprocating pumps. But here we will discuss about the air vessels. Air vessel is a large closed chamber fitted in the reciprocating pump to eliminate the repulsation at the flow of the pipe connected to the pump. On one air vessel is fitted at the edge of the suction and the delivery pipe as close as the pipe as possible, because this reduces the flow fluctuation in the result and rest. This reduces the flow fluctuation in the rest of the pipe length. An air vessel is a closed chamber made of a cast iron steel, and it contains a compressed air contained called a bladder or a bag placed inside the chamber, which is made of synthetic rubber, and its main function is to prevent the loss of compressed air. So we will discuss about some little bit of construction and the working, how the air vessel works. And you can see this is the reciprocating pump, and the air vessels are placed very closer to the pump, and the pump liquid enters the air vessel from the bottom. You can see the sump at the bottom and occupies the lower portion of the chamber, and the air and in this process the compresses the air and the bladder, and when the pressure in the pipeline connected to the air chamber is lower than that of the bladder, the air pressure in the bladder forces the liquid to move out of the vessel. So let the air vessel be located very near to the pump, so that for all the practical purpose, the entire delivery pipe is considered as being affected by the action of the air vessel. In a cycle, there are the two strokes. Like for a delivery stroke, the fluid is being escalated in the first half of the stroke, and the escalation heads is dissipated in the air vessel, and it will be better visible in this diagram. So the escalation has been dissipated in the air vessels, and the less average main flow will pass down the delivery pipe, which until the end of the delivery. At any instant, the flow in the excess of the average will pass into the air vessel and compresses the air which is present there. The pressure in the air vessel will increase, and in the second half of the delivery stroke, the escalation will also be dissipated at the air vessel, and the mean flow pass down the delivery pipe. The process of the flow at the suction pipe, which is with an air vessel is similar to that of the delivery pipe. So the the process is same for the delivery and the suction pipe, but like in the suction pipe, if an air vessel is sufficiently large capacity is fitted very near to the pump, it will absorb all the escalation heads created by the simple harmonic action of the piston in the suction stroke. And considering it will be considered that the frictional losses will be constant along the time, the flow is no more unsteady, and it is necessary that the size of the vessel should be allocated for it to function effectively for a single acting pump. Like for two air vessels, each having the volume of 6 to 9 times the volume of the cylinder, it is as a considered adequate design for a air vessel. Okay. Then we have the indicator diagram. Indicator diagram of for a single acting reciprocating pump equipped with two ideal air vessels, which are air vessels the sufficient capacity and one is suction, and that is pipe fitted very close to the pump. So we can note that the escalation heads for the delivery and suctions are negatively small, therefore they are taken 0. And because of the uniform delivery velocities, the frictional losses are also constant along the respective strokes. So why should we use the air vessels and different strokes? So for the suction pipe, the advantages are like the suction pipe length can be increased, pipe length can be increased, or when the frictional losses are constant, then the power expended is reduced, and for the given reduction and for the speed, the cavitation also reduced and discharge can be increased. And for the delivery, the steady discharge can be assured that the pipe on the basic of the maximum discharge, there will be considerable saving at the diameter, which save also in the cost of the pipes, and it reduces the frictional losses, and which which helps in saving the power, and also it increases the discharge. So here we start the like formulas or analysis of single acting reciprocating pump for air vessels. As you can see, like these are the terms which we are going to use. You can see them. Okay. First we will start. With the velocity. So this is the velocity at the delivery pipe, and this is the average velocity at the suction pipe. And you can see this is a derivation for the average velocity. And then we have the discharge at the we have the discharge where the QI is the instantaneous discharge at the in any pipe, suction or delivery, both are same, only like area of suction into omega r sin theta and area of delivery in omega r sin theta, which is if the area is same, then both are same. So discharge of the air vessel for single acting reciprocating pump is this, and for the double acting reciprocating pump is this, and hence the discharge going in the air vessel is given by this equation. For the single acting, okay, like for the single acting vessel, it transmits only the time average discharge downstream and discharge into the air vessel in a single acting reciprocating pump, which can be expressed like it's here. And for the pressure heads at the suction pipe, there are the two heads which are escalation head and friction losses, and same are for the delivery head. So for this the length LSA, the escalation of the flow in this is confirmed to reach the length LSA from the pump to the air vessel only at the rest of the suction pipe. In the free from the escalation effect as steady uniform flow prevails over there. So this is reaches for the second reach, and there is no other friction losses due to the unsteady flow prevailing uh, between the air vessel and the cylinder. And these average friction losses are given by this formula. And for the delivery pipe, work done by the reciprocating pump with the air vessel, theoretical, this this is this is the escalation head, and the friction losses in according to the Darcy-Webb's equation is this. Okay, and then we have the another friction losses due to unsteady flow, and by using like from this from the Darcy-Webb's equation and the friction losses due to unsteady flow, we can get the average loss of friction losses from the second reach of the delivery pipe is given by this formula. So theoretically, the work done by the reciprocating pump at the air vessel, which is the work done per second per unit weight of the liquid pumped in the reciprocating system, is fitted with the air vessel is given by this formula. And then the velocity has at the suction and delivery pipe is being relatively very small, therefore we neglect these two terms and we get this formula. And then the theoretical work done per second will be this, and also and by neglecting the velocity head and substituting the QT, the simplified equation, we will get this. And for the power consumption, uh, for the power consumption, this is the formula. Okay.
Good morning, sir. I am Ravi, roll number 208. I will start my topic from indicator diagram. Basically, indicator diagram is a graph between pressure head and distance traveling by the piston. An area under the curve gives idea about work done. Mean area under the curve is directly proportional to the work done. Here we are talking about this area J, K, L and M. Area under J, K, L, M is directly proportional to the work done, which we will see in the later slide. Now we will see ideal indicator diagram. Here line JK is suction stroke line, whereas line LM is delivery stroke, and dotted line represent atmospheric pressure. When the piston sucks the water, then pressure inside the piston gets lower, so we can say it is less than atmospheric pressure, and suction head is constant as well. Mean here HS is suction stroke. Suction stroke is less than atmospheric pressure. And if we will talk about delivery head is this HD, which is also constant, but delivery head has to supply water. So for this reason, delivery head has pressure maximum than delivery head has pressure greater than atmospheric pressure. They both are constant. Okay. Now if we will see theoretical work done per second, this is nothing but rho Al N divided by 60 into HS plus HD. Here rho A and N are constant, L is not constant. Here rho A and N are constant, so work done is directly proportional to L multiply HS plus HD, which give the area under the curve. We can see here the area JKLN. Here L is nothing but JK and HS plus HD means this line and this line. Area under to this line is nothing but this. Then this area is directly proportional to the work done we have seen here. Okay, now we will see indicator diagram with acceleration effect and no friction. We will see here the effect of acceleration only. Okay, and acceleration head for suction pipe is this: HAS is equal to LS divided by G into A divided by AS omega square R cos theta, and it is also same for delivery pipe. You can see here HAD is equal to LD divided by G into A divided by AS omega square R cos theta. Then acceleration head is same for both the pipes, suction pipe and delivery pipe, but the difference is there. Here LS and AS are the length and area of stroke pipe, whereas LD and AS AD, LD and AD are the length and area of the delivery pipe. Now we will see the variation of the acceleration head with theta. We can clearly see here HAS means acceleration head is depending upon the angle theta. When theta varies, this acceleration head also vary. We are clearly seeing this. Okay, so if we will check the variation for theta is equal to 0 degree, cos 0 is nothing but 1. For cos theta is equal to 1, then we can clearly see HAS and HAD will got their maximum values, which is nothing but L divided by G, A divided by A into omega square R. For suction pipe, the length and area of suction pipes has been taken, and for delivery pipe, length and area of delivery pipe will be taken. And for angle 90 degree, we can see cos 90 is 0, then whole term will be 0. For theta is equal to 180 degree, cos 180 is nothing but minus 1, then our whole term will get negative value, mean for cos 180 degree this has minimum value. Okay, now area will remain same, mean the area in the ideal case, which is G. The area under the curve J K L M will be equal to area under the curve P Q R S, because the amount of area decreases here is equal to the amount of area is increases here. We can see here this amount has been increases and the same amount has been decreases, then we can clearly see from this that these two and these two are equal. Mean the area didn't change. Okay, and we can also see that there for theta is equal to 0 degree, this has maximum value, and the in the stroke head the value will be add, then this amount of value is added, and for 180 this amount of value has been decreased. Same for the air delivery stroke. For theta is equal to 0 degree, this amount has been increases, and for theta 180 degree, this amount has been decreases, and for theta 90 degree, no change to there. Both values are same. We can clearly see from the diagram. Okay. Now we will see indicated diagram considering both acceleration and friction effect. For before covering this, we will cover the effect of friction only. Okay. If we will talk about friction, the head loss in friction in stroke pipe and delivery pipe is given by HF, which is equal to 4FL divided by 2GD into A divided by A into R omega sin theta का whole square. We can clearly see here in the acceleration head, the head was somewhat directly proportional to theta. Mean if we will plot the graph between this head and this theta, then this will give linearly graph, and we have seen here this linear graph. But if we will talk about friction head, this loss or friction head is directly not proportional. It has a parabolic nature. Then mean the graph here is a parabolic, not linear. Okay. Now we will see the variation with respect to theta. Here also theta will change, then our head loss in friction also changes. For theta is equal to 0 degree, sine 0 is 0, and sine 180 is also 0. For theta is equal to 0 degree and 180 degree, there will be no change, no loss due to friction. But when theta will be equal to 90 degree, there will be the maximum loss. Okay, which is nothing but 4Fl divided by 2GD into A by A R omega का whole square. For the this is the effect of this is the effect this is the effect of acceleration, the change in acceleration, and we can see this effect. And when the friction is changed, we can see this effect. And the net graph show the combining effect. Okay, the graph shown here is showing the considering both effect. Okay, now the theoretical work done in 1 second will be equal to gamma ALN divided by 60 into HS plus HD plus 2 by 3 HFSM plus 2 by 3 HFDM. Okay, now we will discuss about maximum speed of a reciprocating pump fitted with air vessel. Before covering this, we will somehow introduce air vessel. Okay, air vessel fitted close to cylinder in stroke pipe and delivery pipe. Air vessel fitted close to cylinder in stroke pipe and delivery pipe. The purpose of the air vessel is continuous supply of liquid at uniform depth. It also reduces friction loss in stroke pipe and delivery pipe. It also saves considerable amount of work. Okay. It also need to run pump at high speed without separation. Now we will see hmm, we will see HP minimum, which is minimum pressure in the cylinder that is fixed and is mandated not to be exceeded from considerations of cavitation in the suction stroke, and this is equal to this HP minimum. And after solving we got these huge values. This is our values we are looking for. Okay, you can clearly see here. Now we will talk now about general aspect, and maybe this is the last topic from my side. uh, Comparative study of reciprocating pump and centrifugal pump. Okay, the range of operations of both centrifugal and reciprocating pump is indeed very large and varied, and as much any generalization can only be in terms of their basic characteristics. Any apparent disadvantage is taken care of by appropriate technical innovation in the application. The following is a brief list of major differences in these two types of pumps. Okay, then we will somehow classify or differentiate between reciprocating pump and centrifugal pump. Reciprocating pumps and centrifugal pump. If we talk about reciprocating pump, this is the discharge is fluctuating and pulsating, while the discharge is continuous and smooth in centrifugal pump. If we will talk about reciprocating pump, it handle a small quantity of liquid only, and it is meant for small discharge and high head, while centrifugal pump can handle large quantity of liquid. It is used for large discharge through lower head. This is the major difference. For reciprocating pump, flow rate control only through control of stroke length or speed, and for centrifugal pump, flow can be throttle and hence valve type control is adopted. Selection of pump type. A rough guide to selection of the type of pump. Okay, reciprocating pumps occupy a substantial part of space marked for positive displacement pump, which is PDP. Further, it is clearly seen from figure here. From this figure, means this diagram, uh, that the PDPs have a niche space in the high head low discharge category. The region of appropriate choice of radial mix and axial flow pumps are also indicated in this figure. Okay, now this is from my side. Thank you.